We ask, how far do we move along a curve in a time interval delta t, starting at time interval t? Well, we have our r of t vectors that define our two positions along the curve, and we have a delta r vector between these 2 points on the curve. And intuitively, if delta t is small, then the distance that we move is just the magnitude of our delta r. Now, what's delta r? Well, it's r of t plus delta t minus r of t. We're familiar with this. That's just the numerator of our difference quotient. In other words, if we divide this difference by delta t, we get a quantity, a vector that approximates the derivative of the r function, the r prime of t derivative, so that the difference in these two positions is got to be r prime of t times delta t. And intuitively, if we interpret t as a time, delta t is a time interval, then r prime is just our velocity, so we're multiplying our velocity by our delta t, which gives us our change in position, our delta r vector. So now this is an approximation because r prime can change between here and here, so that this delta r won't be exactly equal to r prime of t delta t. But in the limit as delta t approaches 0, the difference between this expression and this expression also approaches 0, so that in the limit this does tell us the rate at which we're changing position, so that we can say that delta s, the distance that we move between this point and this point, is approximately equal to what? To the magnitude of r prime. Delta s is a scalar quantity. It's just distance. It's how far we move, and that we know to be the magnitude of our delta r is our distance, and that's our r prime delta t. And this is equal to what? Well, actually, we're just going to leave it at this for the moment. I'm kind of working backwards. I was going to say that that's equal to our delta r. Okay, now, we've defined average curvature to be delta t over delta s, where t is our unit tangent vector. Now that we have an expression for delta s, this is going to be close to our delta t divided by the magnitude of r prime of t delta t. Now, as delta t approaches 0, this approximation becomes exact for the same reason this one does, and so does this one. So that we can write this as delta t over delta t divided by the magnitude of r prime of t. And in the limit, as delta t approaches 0, the average curvature delta t, delta unit tangent vector over our delta t time over the magnitude of r prime of t approaches the time derivative of our unit tangent vector, something we know how to calculate, over r prime of t, magnitude of r prime of t, and instead of the prime, just to have a consistency in the notation, we know that r prime of t is dr dt. So that this is what we're going to call our curvature, or our instantaneous curvature, or dt dt divided by dr dt.